Hi everyone, thank you very much for coming to my talk. This is a joint work with Rakesh at UPenn. My name is Thanh Nguyen. I am from Graduate School of Management, Purdue University. So the motivations of this paper coming from the study of comparative equilibrium in the economy with indivisible goods. This is a core concept of economics and has a wide range of applications in market design in both quasi-linear and non-quasi-linear preferences. For example, in quasi-linear setting, you can see that auction design often aim for a competitive equilibrium because it's efficient and in the core. And when we don't have money to allocate resources to agents, we use a pseudo market approach. Then competitive equilibrium is a nice benchmark because it's efficient and it's fair when we give agents the same budget. Unfortunately, when goods are not divisible and preferences are not substitutes, then competitive equilibriums often fail to exist. And there's been a very little theoretical guidance on when to use competitive equilibrium in these settings. What do we know about comparative equilibrium with indivisible goods? There's two types of theorems along this literature. The first one say that comparative equilibrium exists when preferences are special, right? So this go back to the result of Crawford school study. Say that when preferences are substitutes, then we have a comparative equilibrium. And the recent extensions of Boolean and Kemper extend substitute to a so-called modularity demand type, which is more general than substitute, but this class of preferences still are very special. The second line of results shows that comparative equilibrium exists in large economy. And the intuition here is instead of depending on the special type preferences, it depends on the fact that in large economy, the influence of single agents on the whole systems is very small. So many applications, however, lie between these two extremes. The limited complementarities exist, and the economy is finite. This is the main problems concerns in our paper. Here is our result informally. Which shows that approximate equilibrium exists where there's a demand and supply mismatch, but this mismatch is bounded by our parameters depending on the preferences that we call delta substitute preference. Notice that our main result does not depend on quasi-linearity, so it can be applied to both quasi-linear and non-quasi-linear setting. The bound is a worst-case scenario, theoretical worst bounds, and in simulation, we see much better bound. And more importantly, this bound does not depend on the size of the economy, as some of the results like Star and Budish on approximate comparative equilibrium. To motivate the notions of delta substitutes, let me start first with the notions of delta improvement in the setting of quasi-linear preference. Okay? So quasi-linear preference is an utility that can separate by the value that the bundle, X is a bundle that the agent gets, and sum of PI, and I in X is the total price that the agent needs to pay for the bundle. So when the preferences satisfy the quasi-linear setting, then Gu and strategy show that the single improvement property going to be equivalent to the substitutes. So single improvement properties say that if X is not an optimal bundle under the price vector P, then there's a better bundle X prompt where X prompt is can be obtained from X by either adding one item, subtracting one item from X, or doing both of these operations. So here, delta improvement is the generalizations of single improvement. Said that if X is not an optimal bundle under the price P, then we can get a better bundle X prompt where the symmetric difference between X and X prime is at most delta. When delta contains 2 equals to 2, this is a class that is more general than a class of substitutes. And you can see delta here capture the degrees of complementarities in the preferences. So here's an example of delta improvement property. We call it a bundle substitute. So assume that we partition the items into groups, and each of these groups have size at most k. If a bundle is not optimal under a price p, then we can change the bundle inside one group or replace that bundle with a bundle in a different group. Here's an example. Currently, for example, if I have this bundle, this is my bundle X, and under the price P is not optimal, then I can obtain an X prime by the following two operations. I can either chain this bundle into, say, all of this item. Okay, I can chain that, or I can delete this bundle and replace it with a new bundle, say, for example, this bundle. Okay, so these definitions really capture the fact that inside a group of items, we can have arbitrary complementarities and externalities, but there is a substitutions across different group. And of course, when the group size is 1, we got the cross substitute. And in general, this class of preference satisfy the 2 times case improvement property. Our results show that if the preferences satisfy the delta improvement property and quasi-linear, then for every supply vector S, there exists a perturbation of S to be S prime such that comparative equilibrium exists under S prime, and the deviation for every good is at most delta minus 1. So this result can be more general. So instead of requiring the preference to be quasi-linear and delta improvement property, we say that if the preferences are delta substitute, then for every supply S, there will be a perturbation of S to S prime such that under S prime there exists a comparative equilibrium. And furthermore, the perturbations is not changing more than delta minus 1 item for each of the good. So what is delta substitute? Now to define delta substitute, I would like to introduce a little bit of a notation. So there's m types of individual goods. Each good has supply Sj. Suppose an agent consumes at most 1 item of each good. This is for purpose of presentation. This in the paper we consider the more generous setting as well. There's n agents. Agent I has a set of bundle xi that they can consume. These are the feasible bundle to agent I. And what we assume about the utility ui xt is that it is a non-increasing in transfer t, and we normalize it to be 0 at bundle 0 and transfer 0. Now, quasi-linear setting is a special case of this class of utility. Non-increasing and continuous. In T. Okay, sorry, I'm missing the continuous. So the choice correspondence of an utility is just the set of bundles that attain the maximum level of utility, and the convex whole of the choice correspondence is denoted by this convex choice at P. So delta substitute we define in 2 different ways. First is the geometric interpretations of these definitions. It said that if utility satisfies the delta substitute, if we look at the polytoph, the convex hull of the choice correspondence, so it's a binary polytoph, and we look at every edge of this polytoph. Okay? So each edge of this polytoph is 0, 1, and minus 1 vector, and the error norm of each edge is at most delta, then we say the utility is satisfied delta substitute property. Yeah, so here you can see two examples. First, say that for gross substitute, the edges has at most 2 non-zero, and additional they are of opposite side. So the L1 norm of this edges is at most 2. The second example says that if agent can consume bundles of size at most k, then the L1 norm of each edge is at most 2k. So therefore, for that class of preference, the utility satisfies 2k substitutes. So here's another definition, which we shows equivalent to the first definitions. This is on the improvement property of the bundles. It says that for any price P and two bundle X and Y in the choice correspondence, if we change the price by delta P, so delta P is the change in the price, such that the change in the bundle X is more than the change in the Y. Okay. Then there exists some item in X minus Y, in X but not in Y, and some item in Y but not in X, such that the number of items in A and B is at most delta. And if we take A from X and add B to X, then we get a new bundle, which is a yellow set here, that is in the choice correspondence again. And furthermore, the change in price of A is larger than the change of price in B. Okay, theorem said that these two definitions are equivalent. Notice that both of the definition does not depend on quasi-linearity. The first definitions based on the geometry of the choice correspondence convex hull. The second talk about the improvement property. Okay, so from these definitions, it's fairly simple to see that why this improvement property is stronger. It's in quasi-linear setting, we can show the improvement property from this definition. So here is a sketch of the proof for the main theorem. This is our main theorem is below here. The third theorem, that is, if the preference are delta substitute, then we can find an approximate comparative equilibrium. To show that, we start from the standard theorems of existing comparative equilibrium in Wu strategy, so that if utility satisfies single improvement and quasi-linear, then we have a comparative equilibrium. Okay? So the first step of the generalization is to get rid of the quasi-linear. By doing so, we said if utility satisfies the generalized single improvement, then there exists a comparative equilibrium. Okay? So the generalized single improvement here get rid of the quasi-linear by focusing on the geometry of the convex hull of the choice correspondence. Let's say that the edges of the choice correspondence convex hull have at most two non-zero coordinates and their opposite side. Okay? And from these theorems, when after getting rid of the quasi-linear property, we fully generalize it into delta substitute. So here a little bit of the sketch of the proof. So if utility satisfies the generalized single improvement, then there exists a comparative equilibrium. So we prove this by convexify the economy by allowing agents to consume lottery. Okay, so when we allow agents to consume lottery, then there exists a comparative equilibrium. And this comparative equilibrium can be captured by a bunch of allocations, x1, x2 to xn, where n is the number of agents, where each of these xi is in the convex hull of the choice correspondence. So these are the zero dot in each of the convex hull. Okay. So using a unimodularity theorem, we can show that if each of these polytopes are nice, the edges have at most two coordinates of opposite side, then we can find y1, y2 to yn that are the vertices of this convex hull that add up to the same vector C. Okay. So this theorem actually is equivalent to the theorem in unimodularity, network matrix, or discrete convexity, or polymorphic summation theorem. And so we generalize this into DeltaSubstitute, right? So again, DeltaSubstitute say that if the edges of this choice corresponding polytope has L1 norm at most delta, we call this delta uniform polytope. Yeah. And our main tool here is an approximate unimodularity theorem. Say that if sum of the xi is an integer vector and hxi is a delta uniform polytope, then we can find xy, y1 to yn, that vertices of this polytope such that the infinity norm of the difference between sum of xi and sum of yi is at most delta minus 1. This result implies that if utilities satisfy the generalizing delta improvement, then there exists a nearby comparative equilibrium because each of these y1, yn now become the integer bundle. Okay, so here's a little bit of the idea inside the proof. So again, we start with a convexified economy when x1, xn belong to the convex hull of the choice correspondent di. The algorithms first going to find the minimal phases of di that contain xi. For example, it's going to find this is going to be the minimum phase that contain that. It says minimum phase contain that, and that is the minimum phase that contain that 0 point. Okay, so we show that either the dimensions of at least one of these di's will be strictly smaller than the original convex hull of demand correspondent, or we can drop one of the supply constraints without violating it by too much. And these procedures continue until all these xi become vertices of the polytope. Okay. So in the paper, we show how to use this result can be applied to pseudo market mechanism without money. We show that how approximate unimodularity can be useful in other contexts as well. Okay, by this, I like to stop here and thank you very much for your attention.